Alright, in this video, we're going over transforming polynomial functions part 2. Our LEQ for this lesson is how do you apply transformations to graphs of polynomial functions. Here's your vocab. Your first definition is a power function. A power function is a function of the form y equals a times x raised to the b, where a and b are non-zero real numbers. Here are a few examples. Y equals 0.5x to the sixth, 1 half x squared, x raised to the 0.25. If you notice, this looks a lot like direct variation, okay? And then our constant of proportionality is simply the letter a, because a will never change in this function, okay? And in fact, it says if y equals ax to the b describes y as a power function of x, then y varies directly with or is proportional to the bth power of x, basically x raised to the power. A is directly proportional to x raised to that power. So that is called the constant of proportionality. All right. So let's look at this example. It says constructing a quartic function with two real zeros. So what is a quartic function with only two real zeros, x equals 5 and x equals 9? And we're going to do this using algebraic methods. Well, the first thing we need to do is take our zeros and turn them into roots. And remember, your roots are always going to be in the form of x minus b. Okay, b being your zeros. So x minus 5 is one, and x minus 9 is the other. Now, we know a quartic has four roots. Okay, we know a quartic has four roots. So we're going to have to find another way to get two other roots here that aren't real zeros. Well, the easiest way to do that is multiply by q of x and make sure q of x has no real zeros. Okay, so make q of x a quadratic with no real zeros. Well, how do you do that? How do you write a quadratic with two non-real zeros? Simple. You do x squared, you do a squared plus b squared, because if you remember the special case chart, a squared plus b squared factors into a plus bi and a minus bi. So both of those come out to be imaginary roots. All right, it doesn't matter what you write here, as long as it's a squared plus b squared. You can do x squared plus 1 like they did here. You could do x squared plus 4 because 4 is a perfect square. You could do x squared plus 9. I mean, you could do 4x squared plus 1 because 4x squared is still a perfect square. So you can really do anything as long as it's a squared plus b squared, as long as this is a perfect square and this is a perfect square. But I would recommend just keeping x squared plus 1 because that makes your multiplication easier. So once you have your two roots and then your q of x, which has no real zeros, you simply multiply your two roots together. So when you multiply the x minus 5 and the x minus 9, you're going to get x squared minus 14x plus 45, and then again times the x squared plus 1. So from here, you would simply do the same thing. You just multiply this polynomial by this one. So your final answer would come out to x squared minus 14x cubed plus 46x squared minus 14x plus 45. This function here is a quartic function with only two real zeros, x equals 5 and x equals 9. How do we know that? Because we solved backwards for the polynomial. We started with our two roots, and then since we know we needed four roots, we made up a quadratic that has no real roots, okay? That's where I got the x squared plus 1 from. Then we just simply multiplied everything together to get our resulting polynomial. All right, to get our resulting polynomial. All right. So I want you to try this one. What is a quartic function f of x with only two real zeros, x equals 0 and x equals 6? So go ahead and pause the video and figure this one out. All right, That should have been enough time. All right, so we know we need to turn these into factors, so we can do x times, because you don't really have to write x minus 0, you can just write x, and then it's x minus 6, and then remember we need to multiply by some q of x, so that q of x has no real zeros. So let's make that, for simplicity's sake, just the x squared plus 1. All right, so now you just distribute this x through, and you get x squared minus 6x. And we are going to multiply that by x squared plus 1. Alright, so x times x is x to the 4th. I'm sorry, x squared times x squared is x to the 4th. X squared times 1 is just positive x squared. Negative 6x times x squared is negative 6x cubed. And negative 6x times 1 is simply negative 6x. Okay, I need to put an f of x out here because that's the function we're creating. Now, since these two terms are switched, I'm just simply going to switch them. So we're going to have x to the 4th minus 6x squared cubed plus x squared minus 6x. Alright, so that is our polynomial, that is our polynomial with only two real zeros, 0 and 6. Again, how do we know that it only has those two real zeros? Well, we solve backwards for it. We have x minus 0, or just x, times x minus 6. Then we multiplied by a q of x that has no real solutions. And that's our x squared plus 1, because remember, x squared plus 1 will factor into x plus I and x minus I. All right, because this will give us x squared, and then, so that's x squared, this is minus xi, this is plus xi, and this is minus I squared. That cancels, I squared equals negative 1. So we have x squared minus negative 1, and of course the double negative here gives you the x squared plus 1. All right, so we know q of x has no real roots, and I just proved that right here. We know x squared plus 1 has no real roots, so then we just distributed the x through, multiplied these two together, got our resulting polynomial, and then wrote it in standard form. Okay, so that's really it for writing quartic functions with a given number of real roots. All right, moving along. Modeling with a power function. So it says wind generated power. Wind forms are a source of renewable energy found around the world. The power P in kilowatts generated by a wind turbine varies directly as the cube of the wind speed V in meters per second. This picture shows the power output of one turbine at one wind speed to the nearest kilowatt hour. How much does the turbine generate in a 10 meter per second wind? All right. So on this one, the first thing we need to do is set up the formula that we're going to use. Okay, so in this case, the formula that we're going to use is P equals, okay, because if you look over here, it says the power P in kilowatts generated by a wind turbine directly is vary as the cube of the wind speed V in meters per second squared. Okay, so P is the power we're looking for. A is the speed. No, I'm sorry, A is not the speed. V is the speed. And of course, A is that constant of proportionality. Now, in this case, we're given P, because we know from the picture, we're given P, 600. We're given V, 8 meters per second. So now we need to solve for A. We need to solve for the constant of proportionality. So what do we know so far? Well, we know that 600, because we're using our formula here. Okay, we're using our formula here. We know that 600 equals A times 8 cubed, because again, we have power equals our proportionality constant times our wind speed cubed, which is what I got from up here. Varies directly as the cube of the wind speed V. All right, so we know P is 600. We don't know A, but we know V is 8 meters per second squared. I mean 8 meters per second, because that's what we have here. right? So then now all we have to do is simply solve for a. So we know 600 equals 512a because 8 cubed is 512. And then of course we divide both sides by the 512 to get a is approximately 1.1719. So now we can figure out what our proportion, well, we found our proportionality constant. So now we can figure out how much power is produced when the wind speeds up to 10 meters per second. Okay, because now all we have to do is rewrite our original formula with a this time. So P is approximately, and the reason this is approximately is because this is a run-on. So P is approximately 1.1719 V cubed. All right. So we want to know how much is generated when the wind speeds up to 10 meters per second. So all we're simply going to do is plug in 10 for V and then cube it and then multiply it by the 1.1719. And when you do that, you get 1,171.9, and it says to how much to the nearest kilowatt. So you simply round it to the nearest kilowatt. So this turbine generates about 1,172 kilowatts of power in a 10 meter per second wind. Okay, so this is fairly simple because you're gonna have to start with, if they don't give you the proportionality constant, they're gonna have to give you P and V. Okay, so then you just plug in P, plug in V, solve for A. After you find A, you plug it back into your original equation, like they did here. Then you can solve the real question that they asked you, which in this case is to the nearest kilowatt. How much power does this turbine generate at 10 meters per second? Okay, so we just plug in the 10 for V, multiply it by A, and then and then round, and we get our answer. Okay, not too bad, not too bad. All right, last thing. Let me move this out of the way. It says another wind turbine generates 210 kilowatts of power in a 12 mile per hour wind. How much power does this turbine generate in a 20 mile per hour wind? All right, so pause the video and solve this. All right, so we're going to use the same equation. We're going to use P equals AV cubed because we're still talking about a wind turbine. So we're still going to use the P equals AV cubed. Now, the velocity to start with, we're going to have to use the 12 miles per hour and the 210 kilowatt hours. So we're going to do 210 equals A times 12 cubed. All right, now we just simply have to solve for A. So 12 cubed is 1728. And then, of course, bring down your A. Divide by 1728. Divide by 1728. So A is approximately 0.1215. Okay. So now we can plug A back into our formula. So now we know that P equals 0.1215 times V cubed. So P equals 0.1215. Now we can plug in our 20 mile per hour wind to see how much power is created. So 20 cubed is 8,000. Whoops. So P equals 0.1215 times 8,000. So just simply multiply that out. We get P equals 972 kilowatts. Okay, you should have got 972 kilowatts. All right, so that's pretty much it for the second half of this video. Feel free to watch it as many times as you need to, and make sure you come to class tomorrow ready to work some problems. See you tomorrow.